Good afternoon. I'm Stephanie Pacheco. I manage the education and outreach programs at the Hopkins Center for the Arts. And we are so thrilled to be partnering with Thayer for this entire project, which is really taking root in a new opera called Tesla in New York, written by composer Phil Klein and filmmaker Jim Jarmusch. And they are old childhood friends and have been long fascinated by Nikola Tesla, and so decided, as they were talking about a collaboration to do together, that they wanted to tackle Tesla. And that started this long research process into Tesla's life and trying to really separate myth and man and fact and fiction. And we were lucky to have Phil here. They're unfortunately not here now because they're in rehearsal trying to get ready for tomorrow night's performance, but we were fortunate to have Phil here on Tuesday for lunch with some of the Thayer faculty and students. And Phil was sharing a little bit about how the opera is really focusing on the emotional life of Tesla. And so he told us this great story that Tesla, his father was a priest and really wanted him to become a man of the cloth. And when he was 13 years old, he grew very, very sick and was on what some say was his deathbed. And by Tesla's own account, he woke up as a child. His father was sitting by his bedside, and he woke up out of a fever in the middle of the night one night and looked at him and said, "Father, if God saves me, can I become an engineer?" And his father, desperate for his boy to live, agreed to anything at that point. So Friday and Saturday night at the Hopkins Center, we will be presenting a work-in-progress concert version of the music of this opera, and that's our first glimpse into the score. But we wanted to take this opportunity to put aside the man for a minute and really look at the emotional man, and look at his inventions and the science and some of the technologies as they apply to modern day. So I just want to take a brief moment and express our deep thanks to Joe Helbley, Dean of Thayer, for really agreeing to come play with the Hopkins Center on this one, to Professors Charlie Sullivan and Ulrika Vext for being our cheerleaders and really helping us push through organizing all the demonstrations with students. Definitely would like to thank Thayer and MIT students who've really dug in and developed the demonstrations you'll see outside in the fair, and Kim Cooper, Aaron Smith, all of the staff that have been helping us with 1,000 little logistical details. And a special acknowledgement to the Office of the Provost and the Office of the President, who have supported this as part of the Year of the Arts at Dartmouth. So without further ado, I'll introduce you to Charles Sullivan, who's Associate Professor of Engineering at Thayer School, where he's been teaching since 1996, and really focuses on magnetics and power electronics. And I will turn it over. Thank you.
We have two panelists and myself today. When I was first planning this, I had a long list of people that I might want to invite, but there were two people who were the ones I was most excited about getting here, and both of them accepted my invitations early, and so I decided to quit there when I had the two best people. And those are Professor Dave Perreault from MIT, and I could list a very long set of, that's not Dave. This is Dave. I could list a very long list of his accomplishments, but I just list him there as being an engineer because that's the side of it that he's representing. He's representing the modern applications of Tesla's legacy and really pushing that legacy forward, not just implementing it. And the other panelist that we have is Bernie Carlson from the University of Virginia, and he's the other side of this. He's a historian, and he's the author of the forthcoming book, Tesla, Inventor of the Electrical Age. And if you're interested in learning more about that book, we do have flyers about it outside. We're originally hoping to have copies here for him to sign, but it wasn't quite printed in time, so it's coming out in about a month. He will actually be back here signing books at the Dartmouth bookstore in May. So I have three names up there, which I like because 3 is Tesla's favorite number. But there are actually only two of us standing here. And we took Tesla's suggestion. Tesla suggested in 1896 that every city on the globe could be on an immense circuit. Thus, a message sent from New York could be in England, Africa, and Australia in an instant. What a grand thing that would be. And so we're gonna try that. We're gonna have Professor Carlson joining us by Skype today. So he will be giving his segment of the talk by Skype. And it looks like we have him on the line there. All right. So we'll start with a view into the technology to give you a better sense of what some of those technologies were and what their relevance is today. And then we'll kind of do this in reverse order. Then we'll go into the history segment.
All right. Thank you. So I'll talk a little bit about some of the legacy, the technical legacy of Tesla, and sort of how it followed on into the modern world. And I'd like to especially explain physically how did a couple of the inventions that he came up with work. Just to set the stage a little bit, and I won't pretend to be a historian, but by the 1880s, it's pretty clear that electricity is taking off, right? You've got Edison out there pushing it, and well before Edison, you had lighting, which was mostly originally arc lights, and then when Edison and Swan and so forth came in, you started having incandescent lighting. You had motors, and mostly over short distances, you had some amount of electrical power distribution to carry energy from one place to another. And this infrastructure base, by the early 1880s, is rapidly growing, right? Edison's putting in Pearl Street Station. Around the world, electrical generations being put in, lighting, arc lighting systems, in some case, machine systems. Now, they have generators, they have lightings, they have motors, so both AC and DC, but really only DC for motors. And why is that? Well, lighting, you're either striking an arc and sustaining it, or you're just heating a piece of wire up until it glows. So you can do that with AC or DC. DC was somewhat more familiar because it was more historically used, including for telegraphy work. And early generators, because of that reason, were dynamos, which really generated DC output using a commutator. So the notion is, look, a machine, let's see if this works for us. A machine, generates voltage based on a changing magnetic flux. So the voltage it inherently generates is going to be AC. But if you have a rotating element and a commutator, what you can do is you can sort of pick off the tops so that you take an internal set of AC voltages and synthesize something that's slightly pulsed DC or even continuous DC. And that's what people did. Now, that was for generating. You could generate AC naturally or DC, and people usually wanted DC from early time because of all the work in telegraphy and other work. And motors were really understood as sort of just a generator or a dynamo, a DC generator, connected backwards to convert electrical energy to mechanical energy. In fact, one of the major people who originally found this, he found it by accident because he was trying to parallel two generators, and one started turning from the other working. And so naturally, if you stick current through a wire, you create an electromagnet, right? And it wants to align, this rotating electromagnet called the armature, wants to align with the north and south poles naturally, right? The magnets will align. To get it to keep going around, then you need to reverse the poles in the magnet. And so they stuck in this commutator, all right, which just basically switches the direction. And here you can see, this is a 50 kilowatt Edison dynamo of the era. Here you can see the commutator. So there's a lot more than just these two connections. There's a whole bunch of connections. But the idea is it was sort of seen as a fundamentally DC thing, that we were just somehow switching things around inside to keep the DC aligned where you wanted it, right? They really didn't have a concept of using an AC machine. They couldn't figure out a way to make it work. Well, this was probably Tesla's single most important big hit, was the so-called rotating magnetic field, okay? And let me just explain physically how this works. Clearly, if I had a magnet and I could create a rotating magnetic field that would go around the periphery, then if my rotor was just a magnet, it would track around in a circle, right? So clearly, if I can create a rotating magnetic field, even with a DC magnet, I can still get rotation. Okay? And so what he did was he realized that, okay, if I take two electromagnets and put AC in each of them, here I have the green one and the yellow one, and I'll put an AC or a sinusoid in each of them. Okay? And the windings are dispersed around in space, right? There's one vertical and one horizontal in this example. And they're dispersed in time, too. I have one that's a sine wave and one that's a cosine wave. And the idea is, if I'm here at this time, the green is highly magnetized, it has a lot of current in it, yellow is not, so that I get a lateral magnetic field applied across the rotor. If I wait a little bit longer, green and yellow are equal, so I've got a direction here and a direction here, and I get this direction. Whoa. If I wait a little longer, green is 0 and yellow is high, so I've rotated up. So as you can see, as these go along in time, the field rotates around. And that's exactly what you need. It's a constant magnitude field that rotates around. That's exactly what you need to induce rotation. And here you can see an example of one of actually Tesla's machines right there with orthogonal windings on it. Now, this was really valuable for a bunch of reasons. First of all, because now if he can generate the two-phase AC, he can make things rotate, and there's no commutator involved, right? And the commutator itself, first of all, sparked a lot. It was a big wear mechanism. It lost a lot of energy. So there were a lot of negatives to having to have it there to begin with. So it's a technical advance in that regard. But he also realized that what you could do is if you took a generator that generated directly this AC by having two orthogonal magnets, two orthogonal windings, ship the currents around, you could make the motor rotate over here. So he realized that you could play the same trick, have a generator in one place, send the energy along, make it rotate in the other, with no commutator on either side. So he's gotten rid of the commutator on the generator and on the motor, so sort of a double advantage there. So he came up with this idea, which is a really important idea, because now you can use AC instead of DC. And then what he quickly did was basically not only come up with this rotating magnetic field, but propose a huge range of machines that essentially span every possible way you could think to generate this rotating magnetic field. All the different machine types that we think of today, reluctance machines, induction machines most importantly. He came up with a notion of a machine that now I don't even need a connection to the rotor. Instead of not only do I not need a commutator, I don't need any connection at all, just a bunch of windings right on the rotor itself, or even a solid rotor he showed you could make rotate. So this greatly simplified the machines. It made them more power dense. It made them longer lasting. Moreover, he thought of, this is a two-phase example, he thought of higher phase systems. So what he did was he had this brilliant insight, and then once he started filing patents, he just expanded it out to cover almost any way of doing that you could think of, and he really locked up the entire field early. Now, why was this so important, and why is it important to us today? And it's not just because the machines and the generators were better. They were. But here's the challenge. If you're a manufacturer, right, you want to generate power, you want to ship it somewhere, and you want to use it. And the two main uses at the time were motive power, motors, and lighting. And heck, except for electronics, that's our main uses today. And what you would like to do is if you want to transmit it a long distance, what do you want to use? You want to use high voltage, so you can use low current and small copper, right? Power is voltage times current. Low current is less copper that you need to prevent losses. And there's a very nice demonstration of this outside. And so because he could transform voltage up, carry it a long distance, because of the existence of the transformer, which he didn't invent, but he did do some work on transformers, but others invented transformers, combined with AC machines, you can now build completely AC power systems. And because of AC, you could transform the voltage down, whereas with DC, it was very difficult to transform voltage levels, and hence, you really couldn't, say put incandescent lighting on high voltage DC. You were stuck with low voltage DC, and hence short range. So the result of this is, because of this invention and his teaming with Westinghouse, they were able to basically build power systems that could extend over long distances, distribute out power and convert it down. And this is precisely what you have in today's modern power system. You generate power, you step it up, you transfer it at high voltage, you use transformers to bring it down, and then you can have AC motors at the other end. Without the AC motors at the other end, well, it's not as attractive a proposition. But the key thing for the legacy is not only, well, that's because we do it that way today. If Tesla hadn't thought of the rotating magnetic field and the way to do it, within 20 years, I'm certain the technology would have come about. But here's the thing. This was just at the pivot point where electricity was exploding. Okay? People were installing capacity left and right to do lighting and machines and everything else. And he came along just in time with his technology to get Westinghouse up and going so that basically people switched over very quickly to using AC. And they were able to do the major installations like Niagara Falls being the big one that everybody remembers in AC. If he had not come along, a lot of that would have gone to DC, and we would have spent a much, much greater time ripping it out and catching up, and we would have been probably much behind technologically where we are today because of that. It would be sort of like if you showed up in 1990 with a brand new way to do the internet, you could have gotten it in there. If you showed up with it today, no matter how good it is, there's so much legacy equipment, it's very hard to put in. And that's something that he provided that nobody else at the time had the insight for. Now, Tesla made this big score, and he moved on from there, and that's had huge repercussions down to the modern AC grid system. His next big forays were in the directions of very high frequencies and high potentials and how to apply them. And he really made a lot of advances in this area. And one of them that you're going to see outside is the Tesla coil. And so I wanted to explain how the classic version of the Tesla coil worked. And what he really did was he used a spark gap as a switch, and he triggered, let's try this again. He triggered a resonance between this inductor and the primary of the transformer winding, LC oscillation, much like a mass spring. So basically, you pull the mass down with the mains and it charges up, and when the spark gap releases, that's like letting the mass go, and it oscillates. So that's a tuned structure. He was really a pioneer of using resonance in electrical phenomena to get the exact effect he wants, and we'll see how he uses this. But not only is this tuned, this is double tuned, because what he does is he links the magnetic flux from this oscillation over to his secondary, which he's able, because it's loosely coupled, it's actually inductive power transfer, contactless, over a big distance between these windings. He's able to build very, very high voltage secondaries, and moreover, he tunes the secondary to also oscillate. So it would be like having another mass spring to which this is coupled, which the mass is much smaller, so it oscillates much farther. Okay, so you can get really high voltages with this. Okay? So he's able to get voltage gains and frequencies that are just unachievable with other techniques that people are using, at least at the time. So he pushed forward with these techniques, and he developed a lot of applications that have become important today. And I think one of them, he was interested in lighting, and he really was the pioneer of the electrodeless lamp, or the plasma lamp, and this is a modern version of that there. Here's that Tesla with one of his. He also contributed to fluorescent lamps, which have electrodes internally, although there were other people working on those as well. But he was the person to develop the plasma lamp. And the notion of this is, if you think about it, heating up a piece of tungsten or whatever your material of choice is until it gets so hot that it glows and emits a little bit of its energy as light is really a pretty barbaric way to make light, right? Where really he's doing is exciting gases directly and letting their energy states fall so they emit that directly. It can be much more efficient. He saw it way back then. That's the reason why most commercial buildings are lit with fluorescence today.
Do we have plasma lamps now?
Yes, we do. There you go. That's a commercial unit right there. So yes, people do use plasma lamps. They're efficient. They're expensive, but they have very long life because there's no internal electrode. Yeah, I'm sure you can go buy one if you'd like. The other way that Tesla's really pushed forward, he was really pushing for wireless power transmission, right? And that's what he's really famous for. Now, his main focus was transmitting energy. That was his dream. But his lectures and his patents also cover sending intelligence or information. And he was one of the first to recognize using resonant tuning to control wireless transfer. And this kind of tuning is basically at the core of all modern radio systems. You really can't practically operate without it. And the idea is using the tuning, and in particularly in his case, using the double tuning, enables you to prevent interference among different transmitters and receivers. So, if I have one station here and somebody wants to receive it, and another station here, somebody wants to receive it, what prevents these two stations from interfering with one another is you tune each of them to only transmit and receive in the space they're allocated to. Now, this idea of tuning is the central concept that lets you have multiple transmitters and receivers. And Tesla really beat Marconi to this concept. Not only the concept of tuning, but double tuning, because if we recall, the Tesla coil, which he was using both as his transmitter and his receiver, is a double tuned system. You have a tuned primary and then magnetically coupled to a tuned secondary. This double tuning was the core of Marconi's famous 4-7 patents. It's one of the most litigated patents in history. He was beat to it both by Lodge in England, Oliver Lodge in England, and in the United States by Nikola Tesla. So I think it's fair to say that, and moreover, a lot of people, including ultimately Marconi, were using Tesla's innovations in how to generate the high frequencies to make progress. So while he really was after wireless energy transfer, he does deserve credit with others for developing tuning as a means of RF communications. And I should say, by the way, that if you have the difference between then and now is if you have a 4G LTE system, you have to put all of your energy in a very, very narrow frequency band and nothing next to it. So to give you again an example of a modern result of that, and the modern result of tuning is that in an LTE system you may have a 10 megahertz bandwidth in which you put in your energy, and the next 10 megahertz over you have to be down by a factor of say 50,000 in the amount of energy you put there. So this frequency selectivity that Tesla was playing with and using multiple tunings to get very high selectivity really is crucial to enabling modern communication systems. Now after that, Tesla was really after wireless power transmission. Do we do that today? Well, clearly inductive coupling is in very wide use today, or inductive coupling across the gap for biomedical implants, portable devices, laptop chargers. You'll see some of these out in the demos outside. That's what Tesla was really doing in his Tesla coil between the primary and the secondary. That's how he was able to isolate the secondary so he could get really high voltages. Also, he was transmitting energy, whether he recognized it or not, by radiated coupling. And at low powers, actually, microwave radiated coupling is sometimes used today. People have done this across very large distances in demonstrations. This is the 1960s. People were using it to fly a helicopter as a demonstration. Here they transmitted 30 kilowatts over a mile using microwave energy. So this is basically exactly Tesla's plan. There are practical applications for it. I mean, one that's been on people's minds for a long time and is sort of the source of, say, this demonstration is the notion of, basically putting energy collection up in space and then beaming it to Earth with microwave transmission because there's no clouds and no night far enough up in space. That's yet to be realized in a commercial sense, and yet eventually we're likely to get there. So he was way ahead of his time. In terms of wireless powered vehicles, people have now are developing right now. The notion is you put a dirigible over a city and you can put your cell phone base station way up high so everybody can get good cell phone reception. If you want to keep it there permanently, you got to get energy to it somehow, right? A wireless microwave power transmitter is a very good way to do that. So, wireless power transmission, less used than he envisioned, but it's still a very real legacy there. Now, he made forays into very many other areas. I think one of the most impressive is really radio controlled, right? He was the first to ever build a remote controlled vehicle. And, he built it for military applications. He was trying to sell it to the Navy. That's clearly been the result we've gotten there is exactly remote piloted vehicles are now the military reality. He was the first to ever do that. And you have to imagine, that was a very impressive thing to do. Not only did he need to transmit information to this thing, he had to build a box that knew how to interpret that information and act on it. With the technology of his day, that is truly, truly astounding that he could do that. I mean, basically the guy had wires and insulators, and that's about it. Okay, so very impressive result. He was also, by the way, among the first to promote medical diathermy, the notion of using RF fields for heating for treatment. He was one of the progenitors, not the only one of this idea, and this is modernly practiced in the modern world for various medical and therapeutic applications. He was also, I will say, into lots of other uses for electricity for therapeutic purposes that are probably kind of crazy by any modern standard, and he didn't necessarily distinguish between those, but there are very real uses to this. And the last thing I'll say, I would say, is the final legacy of Tesla is really the inspiration he's yielded for engineers across the world. Like, you can't throw a stone without hitting an engineer from the former Yugoslavia that doesn't work on RF or power because of this. And it's been engineers everywhere across the world. My colleague, Babak Fahimi, a professor at University of Texas, Dallas, originally from Iran, if you walk into his office, this is what you see, about that scale, hanging in his office. It really, I mean, Tesla was a person who really thought big, he worked really hard, he had no fear of setbacks or failures. If he did, he didn't show it, he kept pressing forward, and he accomplished tremendous amounts, and he didn't let the naysayers stop him. And I think that has always captivated the entrepreneurial and the engineering-oriented. And I think that, in addition to his technology, is one of his really big legacies. So now I guess I will step back and we can hear more on the history side instead of the technical side.
Okay, thank you. Let's thank Dave for that. So that gave us some idea of some of the technologies and hopefully made you more curious about who is this guy Tesla, where did he come from, what motivated him, how did this all happen? And so to talk more about that, we hopefully have the ability to get up on the screen. Ah, look at that. Tesla would be proud. This is Professor Carlson from the University of Virginia, actually literally from the University of Virginia today.
Well, thanks, Eric. We're pleased to be speaking to you, and I'm only sorry not to be able to see the demonstrations that you have out in the foyer. I'm a great lover of actually getting my hands on certain things and playing with the apparatus and learning from them. So you've got a great opportunity today, and it will be a nice compliment to the opera that you're going to hear the musical score from tomorrow. I regret not being able to hear that as well. What I'm going to do is I'm going to talk a little bit about some of the historical context for the inventions that Dave just described. I'm going to use a slide deck that I have here that you'll be able to see in just a moment, and I will jump over some slides. If there's something that I have on a slide that seems to go flying by and you want to ask me about, by all means do so in the Q&A period. But I do want to focus on a couple of basic points about sort of Tesla's background and how he came to some of the inventions that are so important and have shaped our lives since Tesla's time. So as Charlie told you, I've just finished a book which is coming out with Princeton University Press, titled Tesla, the Inventor of the Electrical Age, and the book will be in the you can already order it from Amazon.com. It'll be in the warehouse the 17th of April, they tell me, and I'll be at Dartmouth at your university bookstore to sign books on the 4th of May. Now, what's interesting about that book is I developed when you're a historian and you're a biographer, you don't want to do, as my professor used to say, just tell you one damn thing after another. You try to figure out a trajectory or a path by which you were able to make sense of your subject's entire life. And the principles that I use to think about Tesla's life are these notions of ideal and illusion. And his life is really these two things in tension. So I want to talk just a moment about those and then talk about some of the specific inventions that he came up with. So on one hand, Tesla believed that there was a fundamental principle that could be found hidden behind every major invention, and that the role of the inventor was to discover that principle and exploit it. And he came to this idea, I think, very much as a result of, as someone pointed out a few moments ago, his religious background. His father was a priest in the Serbian Orthodox Church, And basically the Serbian Orthodox Church, which is like the Greek Orthodox, or the Russian Orthodox Church, takes a view that there really is a logos. There's a logic behind everything that we find in the material world. And so Tesla really gets into this notion, I think, as a young man, that there are ideals that can be discovered, and that's his job to do it. And I always like this quote that he said towards the end of his life: "My ideas are always rational because I am an exceptionally accurate instrument of reception." And in many ways, he disciplined himself to be that kind of receiver of these ideals and these principles. Now, the second half of this is there's ideals and then there are illusions. Unfortunately, as Tesla could be much like like the philosopher Plato, he could really understand the ideal. He could grasp that in his mind. But not everyone around him always could fully understand the ideal that he was driving at. And so if you want to engage people about an ideal, you often have to give them some sort of an approximation of the ideal. And that's what I mean by an illusion. You tell them a story, you give them a demonstration, you use a metaphor. There are any number of ways that you can express an ideal, and Tesla used illusion. Now I want to emphasize that in some ways Tesla is not tricking people. He fully understands that he's got to come up with ways that people are engaged by the possibilities of his great ideas. And so he's not being a trickster when he does this. He is a little bit being like a magician, and so a lot of times people talk about Tesla as a magician, and there is something powerful there. And so the driving force of the book is this tension between ideal and illusion, and in particular, as you'll see, as I tell you a little bit about his work on wireless power, I asked that question that's at the bottom of the slide: did Tesla's illusions really get in the way of his pursuit of ideals? So, but that's kind of the question at the end of my remarks. Now, let me tell you a little bit about Tesla's background, and then I want to plunge in and tell you about the specific invention. He was indeed born in 1856 to a family living in Serbia. At that point, they were living in what is modern-day Croatia, but at the time was the military frontier of the Austrian Empire. And so Tesla's family, one side of the family are all soldiers, and the other side are priests in the Serbian Orthodox Church. He was the second son in the family, and in many ways he was challenged by the fact that his parents actually thought that his older brother, who died in an accident, was going to be the sort of shining star of the family. And when the older brother dies, his name is Dane, Tesla really goes into a very difficult period basically when he's sort of 10, 11, 12. And he has terrible nightmares, and the nightmares are very vivid. And he really has to wrestle with a way to cope with all of these powerful images that he's seeing. And the way he does this is he really takes control of his imagination and develops his willpower. I mean, this was somebody who could really focus on certain goals and certain activities. And this stood him in great stead as an inventor because he really was able to imagine things in his mind's eye and then move and develop them in the real world. It is not entirely true that he never ever used any sketches, that everything he built worked exactly the right way the first time that he developed it, but he did have a powerful imagination. And I think that it was both his strength and also his Achilles heel, because the driving force for him was if he could imagine it, he wanted to see that it could be demonstrated in the real world. And even a small amount of evidence that something that he had imagined worked in the real world was a powerful incentive for him. So let me talk first about the AC motor, and then I'm going to talk about wireless power. Tesla, as a young man, does, thanks to his father, go off to study engineering at the Johann Polytechnic School in Graz, Austria, and there he sees a demonstration that Dave was telling you about of connecting two dynamos together. One dynamo is generating electricity, and the other is consuming the electricity, functioning as a motor. And this was a popular demonstration in the late 1870s. And when Tesla's physics professor did it, Tesla piped up and he sort of said, "Why is it sparking so much? This is ridiculous." And he said, "Oh, I'm going to come up with a motor that runs without a commutator." And his professor, of course, at that point laughed at him and said, "Oh, this is like a perpetual motion scheme." and as a result, trying to convince Tesla not to pursue it. Tesla, of course, being a determined young fellow, decides that he is actually going to do it. And he works on this idea for a number of years. In 1881, while he's working in Budapest as a telegraph engineer, he has a vision of a motor that is going to have no commutator, it's going to be sparkless, and it's going to work on the ideal of a rotating magnetic field, which Dave described for you a moment ago. Now, it basically, once he had the ideal, it took him a number of years, from 1881 to 1887, to figure out how to actually how to realize that ideal, how to build the motor that you see over there, and I'm hoping I can wave to it, the motor in the lower left-hand corner there. That's the motor that dates from 1887 and is the first demonstration that he had. But it's a long journey from 1881 to 1887 to get that motor, and in part it depends a lot on his ability to get some very skilled business partners, a man named Charles Peck, and Alfred Brown in New York. Now, the way he got to this alternating current motor, he had the ideal that it was going to be a rotating magnetic field. And the rotating magnetic field was going to take place inside this coil or donut that you see over here. So this is the demonstration motor on the left-hand side, and over here, all this stuff, which I'll talk about in a moment, is the AC generator. Now, to make a motor work, and again, I'm simplifying greatly, but building off of what Dave just said a moment ago, you have two sets of magnets in a motor. You have a static set or a stationary set, which in this case are the four coils that are constituting the donut. And then you have the armature or the rotor, which is in the middle. Now, an electric motor simply works by the fact that you manage at any given moment to have two opposing magnetic fields so that the fields are always pushing against each other. In all the motors, and both DC and AC, up to the time before Tesla, everybody said, well, the way you get this done is just you change the magnetic field in the armature or the rotor. And Tesla, his insight in 1881 is he said, the heck with that. What I'm going to do is I'm going to change the magnetic field in the donut, in the rotor, in the stator. And so that was his really big insight, was to think in reverse. Now to get there, and this is why it took until 1887, is what kind of electricity do you put in the donut? And the answer is you put alternating current in, and you put the alternating current in 2 or 3 phase. Now this particular setup here, which comes from Tesla's lecture in 1888, you've got an alternating current generator over here, an alternator, and you see that you have 4 slip rings, and each pair of those slip rings delivers a different alternating current. So this is a 2-phase system. And Tesla's insight was to figure out that you really needed these two separate currents going into the motor, into the rotor, by having them be 90 degrees out of phase. Okay? And as a result of that, you wind up creating a rotating magnetic field, sort of, if you will, as Tesla sometimes said, a rotating whirlwind going around and around in this donut. And that carries or induces a magnetic field that is opposed in the armature of the stator, and the stator goes round and round. One of my favorite things about this I'll tell you 2 things about this particular motor that he came up with. The first is the very first motor that he came up with in 1887. What he put inside the donut was a shoe polish tin, and it was a tin can, and he had it on a pivot right there, like a thumbtack, and he dropped it in, and lo and behold, the tin can started turning round and round. So he shows this to his backers, the businessmen who put up the money for this, and they look at it, and I'm sure that their attitude was, let me get this straight. You've spent all this time, like a year working on this, and what we have to show for it is a tin can spinning? And the solution, Tesla went away, and of course he was dejected. And what he did is he realized he needed a better representation, a better illusion to capture the imagination of his backers. And the Edgar Columbus apparatus that you have out in the lobby is the apparatus that he came up with. What he did is he again took that big donut coil, he basically bolted that to the bottom side of a table, put a nice green cloth over the table, so you weren't focusing on all the wires for everything. And then he went out and he bought himself a couple of copper eggs, sort of like Easter eggs. And he then went back to his backers and he said, you know the story of the egg of Columbus? And the backers said, yeah, we know the story of the egg of Columbus. Essentially, Columbus got the money from Queen Isabella and King Ferdinand to sail to America to buy the ship, because basically Columbus showed how you could make an egg stand on end, and basically made a fool of all of the people in the court of Ferdinand and Isabella, all the scholars. Looked like fools because they said you couldn't make an egg stand on egg, and Columbus did is he took the egg, he whacked off the bottom of it, and he made it stand on end. And so Tesla says, if I can make an egg stand on end, help me develop this motor. And the two backers say, sure, we'll do that. So basically he invites them over to the laboratory the next day, and he brings them in, and there they see the egg sitting on the table on the green cloth, and he turns on the electric power and gets a rotating magnetic field going in the donut, and sure enough, as you'll see in the demonstration, the egg starts spinning and it stands up on end. And that's why they decided to support Tesla's work on alternating current. So, as I say down there on the bottom, and as Dave emphasized, Tesla's development of alternating current resulted in the AC, in particular the induction motors that we use everywhere today. Now, one of the things that is important to realize, and the last thing I'll say about the motor here is this is back to the 4 wires. Everyone before this basically thought that what you wanted to do is have a minimum number of wires from your generator to your motor, okay? And that the first time that various people saw Tesla's design for the motor, they just sort of said, this is craziness. Who wants to build a system with 4 wires when we should ought to try to get away with 2 wires? And then Tesla worked out solutions for that. But in the end, the earliest designs were really used a lot of copper, and so they were more expensive in a certain sense than the motors that were developed by the motors or the lighting systems developed by Edison and other folks. Now, once you've developed Tesla basically develops this motor that I just showed you in 1887, patents it in 1888, does a series of lectures on it, and then sells the patents to Westinghouse, and Westinghouse goes on ahead and develops the entire system. It takes Westinghouse Westinghouse engineers another 5 to 7 years to make it fully functional. But that's a whole other story which I don't want to get into. But Tesla basically goes to the Westinghouse plant in Pittsburgh, works there for about 8 months, and then he says, "To heck with it! I don't want to work for a company." And he leaves in 1889 and takes the money that he's earned there, and he goes off to the Paris World's Fair, the Paris Exposition of 1889. And there he meets a graduate student that is studying with Heinrich Hertz, and he hears all about these experiments that Hertz has been doing that are about detecting the electromagnetic waves that were predicted by Maxwell in his theory. And in particular, because I want to talk a little bit about the Tesla coil, let me go over here. I hope you're seeing what I'm pointing to here. Everything up here, this big induction coil, which is essentially a transformer. You've got a telegraph key, you've got a battery here, you've got K and K prime, or the antenna. All that's the transmitter in Hertz's early apparatus. And down here, this thing that looks like a big earring, L, is essentially the receiver. And what Hertz's genius was is he walked around his laboratory with this thing going on, running, and interrupting the signal. And every time he interrupted the signal, he induced a spark across here, and that spark created radio waves or electromagnetic waves that could be detected again across this little spark gap in the receiver or the earring. Now Tesla looks at all of this and says, "Man, this is really cool." And he goes back and after he's been to the Paris World's Fair, and in 1890 and 1891, he scales up Hertz's apparatus. And the way he comes to the Tesla coil, which Dave gave you a wonderful description about being a double-tuned resonant device, is he basically reworks the Hertz apparatus that I showed you a moment ago in a way that he gets the maximum high voltage, high frequencies that he was interested in. And so he starts thinking about that. Curiously, and I can tell you more about this in the question and answer period, is as Tesla became convinced that the waves he was generating were more like sound waves, that they were transverse waves as opposed to longitudinal waves. And so as a result, he had to go tell Hertz in about 1893 that Hertz was wrong. Needless to say, Hertz wasn't real happy about that. Now, if you're Tesla, you're not thinking like a scientist. You're not thinking like Hertz. You're not worrying about publishing articles about this. You're saying, where's a new business opportunity where I can take advantage of this new high-powered coil that I've developed? And Tesla always called it his oscillator, or his magnifying transmitter. So the major application where people, for electricity, that was the sort of high-tech, cutting-edge business opportunity was really in lighting. And Tesla thought, man, if I can come up with a lighting system that I can compete with Edison's incandescent system. And again, as we've pointed out, the incandescent system is a very, very, very inefficient way of producing light. Maybe about 5% of the energy that is produced at the generator side actually ever really winds up being used in lighting. So Tesla looked at Geissler tubes, which were around at that point, and basically realized that if you've got gas at a low pressure inside that tube, you can get that tube to glow when it's either connected to an electric current or it's placed in a magnetic field. And one of his great demonstrations was in 1891. Before the Electrical Engineering Society at the time, the AIEE, at Columbia University, Tesla basically got up and he did this demonstration with essentially his Tesla coil sitting somewhere over here on this table, and it's connected to these big zinc plates. Now, this of course is done with the lights on. The lights were turned off. Tesla stepped between these two plates, holding what are essentially modern fluorescent tubes, and the tubes glowed wirelessly in the dark, which just absolutely amazed people. They had not anticipated this sort of action at a distance and transferring this much power. And Tesla went on to describe this entire lighting system whereby you'd have metallic wallpaper and you'd have no wires to your lights in your house or your living room. And you would basically have these tubes and you would just rotate them around so that they would align in the field. That was his idea for wireless lighting. And it was indeed, as Dave pointed out, it was truly a induction coupling system. And this was one of the diagrams that drove me crazy until I finally fully understood. Down here is what Tesla's laboratory looked like. And the induction coupling takes place between a single primary winding or coil that is up here going all the way around the ceiling of the laboratory. And that's the primary, and the secondary, where the power is delivered to, is this thing that looks like a big fat round coffee table, but it was actually on wheels. And that round thing down there is this tuned secondary with adjustable capacity. So this thing right here that's in the diagram, you think, oh, that probably doesn't, that's sitting right there. That moves all around the laboratory. So Tesla studied it. Okay, so this is, and there was an induction coupling. In other words, power was transmitted, where the power was delivered first to the primary up here in the ceiling, and then it was inductively coupled or transmitted to this as, if you will, the receiver. And I love this picture in the next diagram, or the next slide. Whoops, we go there, not yet. There. And that is indeed Mark Twain in Tesla's laboratory in 1894, and he is standing just behind that round coil, and he's got the hula hoop in his hands, if you will, another coil, and the power is being inductively transferred from that coil down here into the hula hoop, and it is lighting up that bulb, which is basically sitting between his hands. Now, this was all a great idea, but Tesla, between 1893 and 1897, is never able to attract any business investors to this particular new system of electric lighting. And it really would have been the third generation of electric lighting. And we never have actually gone to the third generation of electric lighting. Arc lighting was the first. Edison's DC incandescent lighting was the second. and this would have been the third generation. And you know, for whatever reason, but particularly because of the business situation in the mid-1890s, companies like Westinghouse or General Electric were just not going to invest in the third generation of electric lighting. They had already made far too many commitments to it, to the existing incandescent lighting system. So Tesla basically is unable to come up with anybody who's going to invest in this new system. So this prompts him to say, I'm going to move from wireless lighting to wireless power. Now, he went back and he thought about what Maxwell had to say about electromagnetic waves, that electromagnetic waves in the radio frequency portion of the spectrum are the same as light waves. And that, you know, we know that light waves travel in straight lines. So Tesla said, well, these radio waves are going to travel in straight line. And so the bottom line is you're not going to get a whole lot of energy to go from point A to point B, because a lot of it is just going to get scattered as the radio waves emanate from a transmitter or an antenna in all directions. So Tesla decided that the way around this problem, and this point that I make here on the bottom of the slide over here, is that minimize the electromagnetic waves that are coming from your transmitter and maximize the ground current. This was his really central insight about wireless power, and you know, for better or for worse, that's what he decided to do. So to understand this, I've got to show you this little diagram here. The top diagram up here is what everybody else thought. Okay, so if you're Marconi, you've got a transmitter. You basically maximize the amount of electromagnetic energy that's going up to the antenna. The waves travel through the atmosphere, meet this other antenna, come down to the receiver, and you either have a signal picked up there or some energy picked up there. And you complete the circuit by having both the transmitter and the receiver grounded. Now, Tesla was, like I said, with the electric motor, was a real maverick. If everybody's going in one direction, he's going to go in an opposite direction. And here again, he really does. And the lower diagram is what Tesla was thinking. So he said, the real thing to do is to maximize the ground current. So you basically send an oscillating current from your transmitter through the ground, through the earth, and then it gets to the receiver, and you more or less have some kind of return circuit in the atmosphere. Now, he was able to pretty much, while he was still working in his laboratories in New York, kind of figure out what was happening down here in the ground portion of the circuit. What he didn't really know for a long time was what was going to happen up here in the atmosphere. And he really puzzled about that in the late 1890s. What he finally decided was, this is his big blockbuster major patent on this, and so this is the transmitter here, and this is the receiver. What he finally decided was, the energy travels from the ground over here, from the ground on the transmitter to the ground on the receiver, comes up, runs the lights, runs the motors here, and then you have some sort of circuit completion that happens up here. These are balloons, D and D prime. But what goes between here is if you're high enough up in the sky, you are not worrying about radiation or waves traveling from one balloon to the other. It's a matter of conduction. Okay, so Tesla, for better or for worse, decided that this is conduction instead of radiation that happens up here. In other words, a current. If you have a low enough pressure in the sky, basically can jump from here to here. So his big system, as he envisioned it, was going to mean that you were going to have a wireless power system with lots and lots of balloons on long wires tied to towers. So to figure out exactly how this is all going to work in the ground and in the atmosphere, Tesla goes to Colorado Springs. Okay, and if you've seen The Prestige, the movie with David Bowie, you've seen at least Hollywood's version of Tesla at Colorado Springs. And there are some real kind of crazy things that they assume. That beautiful scene in the movie where there's 200 light bulbs being powered by Tesla's giant Tesla coil or magnifying transmitter never actually happened. Okay, but he did produce 100-foot sparks or artificial lightning bolts that basically went across his laboratory. And this is a picture. It's a double exposure where there's Tesla sitting. That was the first exposure in the experimental station. And then they cranked up the system and they generated the lightning bolts that you see there. Tesla was extremely pleased that he was able, when this transmitter was running, inside the experimental station, that out in the fields surrounding the laboratory or the station, he was able to put another coil out there that served as an antenna, if you will, and could get this little light bulb to light up. Okay, and he had several of these demonstrations. One of the things is curious about this is he never tells us in any of the articles or in his research notes how far was the distance from this transmitter to this apparatus. Because as far as Tesla is concerned, if it worked on a small scale, it would work. It would scale up to a high level, and he didn't really need any fancy demonstration. All he really needed was to show you these splendid pictures, and this is one of 50 beautiful illustrations that Tesla did while he was at Colorado Springs that show you the power of his transmitter. So Tesla returns from in January of 1900 to New York and is determined to fully develop his wireless power system. And to do so, he approaches J.P. Morgan, the famous Wall Street financier and banker, and Morgan decides to take a flyer on Tesla and agrees to loan him $150,000, which Tesla then proceeds to use to build this station on the north shore of Long Island at what is today near Shoreham, Long Island, but at the time was called Wardenclyffe. And this was the power station, and this was the transmitting antenna. Now, as I said, the trick is not to send radio waves beaming off of this tower as much as it was to pump energy into the earth. And so Tesla basically, along with the tower, had a 120-foot deep shaft underneath the tower with pipes that were, in his words, able to get a grip on the earth and shake it. Now, he works on this from 1901 to, for the next several years. But in December of 1901, Marconi beats Tesla to the punch. Tesla promised that what he was going to do with this plant was he was going to transmit power and signals, power and intelligence, across the Atlantic. Well aware that this was going to be the sort of killer demonstration, Marconi, who had begun experimenting in 1895 as a young man at his father's house in Bologna, Italy, with wireless telegraphy. In 1901, Marconi essentially decides that he better be the first to transmit across the Atlantic. He needs to get one over on Tesla. So he basically has built for himself a powerful station in Cornwall, England, and then Marconi goes to St. John's, Newfoundland, and on December 12th, Marconi hears 3 faint dots that represent the Morse code S. And I love this picture of Marconi that I have here on the right. That is Marconi looking very, very satisfied, having just heard these signals and basically sending a message across the Atlantic. So you've got money for Morgan, you've spent the $150,000, and somebody else has scooped you. So what do you do? What do you tell Morgan, your patron? Well, you basically come up with an even bolder vision or illusion of the possibilities of new information systems. And Tesla proposes in January 1902 to Morgan that he is going to create a world telegraphy system. He's going to have a few power plants near major cities. Each of them are capable of sending messages to every part of the world. They're going to send those messages by basically beaming, signals through, not beaming, but basically transmitting signals through the Earth's crust. And then everyone around the world will have a small receiver no bigger than a pocket watch. This is the moment where if I was actually there, I'd very quietly take out my cell phone, show you my cell phone, and then put it back in my pocket, because I want you to think about that. And his quote in his proposal to Morgan about this is down at the bottom. Tesla wrote, "The whole world, the whole earth is like a brain as it were, and the capacity of the system is infinite. You see, Mr. Morgan, the revolutionary character of this idea, its civilizing potency, its tremendous money-making power." And in many ways, what Tesla is proposing, that you're going to send all the message, all the information from newspapers, stock reports, telephone calls, every form of electrical communications through this system is a bit like an early World Wide Web. Okay, so Al Gore may not have invented the World Wide Web. Tesla needs to be figured into the story. Now, to just underline what he had in mind, this is a newspaper story from a New York newspaper, the New York American, from 1904, and there's his tower, and people are receiving messages by basically just sticking a pole up in the air. So here you've got somebody out camping, and they just stick up a pole in the air, and they can pick up signals from Tesla's tower. Somebody is out on a sailboat, and they basically through the mast of the sailboat are picking up signals. But my all-time favorite is the socialite is basically sticks up her umbrella into the sky, puts it up as an antenna and receives a signal. Of course, now she's also, which you can't see, is hidden under her dress. It's just she's grounded as well, because remember, the system is going to be basically, despite the way that the artist has drawn this, is the power is going to go from the through the Earth's crust, to the wire under her dress and up that way. But you've got to finish the circuit by holding up your umbrella. Well, despite this grand vision that Tesla had, in 1903, Morgan decides to not give Tesla any more money and withdraws his support. And Tesla is never able to get additional funding to make the entire process go forward. And while Tesla had enjoyed about 20 years of great press coverage, beginning in about 1903, he came to be branded, both the popular press but also in the engineering press, as a visionary and as a poet, that he had these great ideas, but he never really delivered on them. And this really interfered with his further success on this project. But the final point that I want to make about wireless power is we need to think for a minute how it would have actually worked. Now, the way that I explain this is there are two ways of thinking. Is the Earth, when it functions in an electromagnetic sense, like a water balloon, or is it like the ocean? Okay. Now, if it's a water balloon, which is what Tesla is proposing over here on this diagram, it means that if you pump energy into the system. Here it's a mechanical system. Of course, he's got an electrical system. And you start pumping here at a steady rate, which is the resonant frequency of the Earth. Then at a certain point, every time you pump this in, you'll get water squirting out of these little one-way valves all over the Earth. Okay? And the system is great. Now, that does presuppose that the Earth is filled with an inelastic medium that transmits the electromagnetic currents. As it turns out, the Earth does not function like a water balloon. It functions like an ocean, so that when you drop a stone on the edge of the ocean, the waves eventually peter out and do not go from New Jersey, where I grew up, all the way to Spain. They actually disappear somewhere a few hundred yards out, or maybe even a few hundred feet out from the shoreline. Okay, but Tesla always thought that the Earth was going to function like a water balloon. That is not. His exact analogy was a football that you pump up with air. But essentially, he thought that the Earth was going to function like that, and he never really understood why he didn't get the results that he wanted, and that pushed him over the edge. And by about 1905, he has a nervous breakdown, and he's never quite the same again. And so this is a little bit more about the nervous breakdown. So, many people ask me, so what did Tesla do, contribute to radio? Okay, if we're thinking about radio as a broadcast medium, okay, that is to say the sort of box that you have, in your house that basically delivers radio programs to you, AM, FM, then Tesla did not invent radio, okay? Despite many people who want to argue that he did, he did not invent radio, okay? Tesla was, however, the first to experiment with electromagnetic waves, and he wanted to create a useful technology from them. And as Dave pointed out, in doing so, he really set the groundwork for our understanding of how to take advantage of resonance and to use resonance and tuning in very effective ways. And both Marconi and other people that followed up from Tesla took full advantage of what Tesla really understood about tuning. And his story, in many ways, underlines how hard it is to introduce a new disruptive technology and to actually get it to work the right way when you want it to. The rest of Tesla's life is rather sad. From the 1900s to when he dies in 1943, He's very basically poor. He moves from hotel to hotel in New York. In order to get attention at the very end of his life on his 80th birthday, he announced that he had a particle beam weapon for shooting down airplanes, which got a fair amount of press coverage at that particular time. But at the end of the day, my sense is it wasn't a very practical, or was not an all practical device. But there are people today that are still convinced that Tesla did actually come up with this incredible weapon for shooting down airplanes. So let me stop there. I appreciate your patience with me, and I hope I've given you some historical context about Tesla. And I'd be glad to, Charlie, go to some questions or whatever is useful for the audience.
Okay, thank you very much. And I also want to thank both Tesla and Jared Benedict for making the technology work to have him transmitted to us. Okay, since we're running a little bit longer than we had planned, what we're going to do is we're going to give you an option. We have a bunch of demos outside, and in fact, if we can switch to that screen, I will just show you the list of what we have out there. We have a hydroelectric powered high voltage power transmission system. We have an induction motor. It's actually more like Tesla's first demonstration of spinning a tin can. Well, it's actually an aluminum can. So unfortunately, we have the low-grade demo that didn't convince the investors rather than the flashy one that did. We have a remote-controlled model aircraft. We have LED wirelessly powered disco ball system that I'm not sure I completely understand. We have parked out front, we have a Tesla Roadster, which is a vehicle that is powered by Tesla's induction machine as well as using his name. We have 3 Tesla coils, including one from a startup company, Tesla LLC, that is offering kits if you are inspired by it and want to build one yourself. We have a station where you can wirelessly charge your cell phone or watch it charging somebody else's cell phone if you don't want to get your cell phone involved. We have food and drink. We have flyers for the new book. Here's one of them, but we have a stack of them outside. So after listing all of those things that are outside, I'm not sure I'm going to convince any of you to want to stay here and have a conversation. But we will be here, and we will keep this Skype connection open. If some of you want to stick around, maybe move down to the first 5 rows, we can have a 10-minute question and answer period, and then we'll be joining everyone outside.
What's this thing?
So we also have a demonstration here that is a very simple radio transmitter and radio receiver demonstrating that tuning concept for receiving that radio signal. Very simple concept, but absolutely fundamental for all of radio.
We want to see it.
Okay, maybe we'll run that demo while maybe some of the people are eager to get to the demos, and we'll do that as a transition and then take questions.
I don't know what else you need.
My name is Sean Butler. I'm reporting with the D. Unfortunately, I got here 5 minutes late, so I didn't get your name.
Ah, okay. I can write it for you if that's easy.
That would be excellent. And I also want to know who is the kind of founder or organizer of this lecture, and who I should talk to about that. This guy over here.
Professor Sullivan.
Excellent. And I'll be around.
And he's organizing the demonstration. Okay. There are others he's working with that are organizing the whole opera and everything.
All right, cool.
I'm not hearing anything, but I don't know if there's anything else I
may have
need to
messed
do
with
to
the
turn
tuning.
this on.
So do you want to run the?
Yeah, just hold it down.
Oh, and did you turn the power on? You did. Good. Transmit continuously. Just hit.
I'm just holding it. There you go.
So if you.
So there's an adjustable capacitor there. We just adjusted that capacitor in order to get that signal.
And if I off-tune it, you don't get it because it's tuned to some other person transmitting. If we bring the capacitor on, you get this transmitter signal. So this was the magic of tuning. that Tesla was playing with in order to sort of make it so that you can't only have one transmitter and one receiver in the whole world. No receiving, tuned on, tuned off the other way. And that's basically what's at the core of any AM system or any RF system.
So if somebody stands between those two, what happens?
Oh, it'll still work.
Okay, and we put that demo here because it's the least impressive demo, and we needed to give it some patter in order to make it at all appealing. But the demos outside should be more impressive. But still, we're now available to take questions. So I'll ask the people
How does it work for single phase and household current?
who have
Very good.
questions.
So there's always some mechanism to start it. So once you
We're going to have a group session here. So maybe if you'd like to state your question, I'll repeat it for the audience.
I understand how the multi-phase motor works for AC, but how does the single phase work in a household current?
Okay, so the question is, we explained how a multi-phase motor works, and the question is, how does a single-phase motor work? And in fact, the induction motor that we have demonstrated outside is a single-phase induction motor. And I don't know, Dave, do you want to take that question?
Okay, yeah. So the way to do it is you cheat and make some way to take that single phase current and generate at least some second phase. So one of the ways he did it, for example, and I believe you said that was a shaded pole motor, is you make something that will create some lag. So some energy storage and dissipation circuit that will create a second field that may be much smaller with some lag, and that gets the motor started. And once it locks on position, it can kind of ride through the nulls of only having one major phase. So one of the contributions that Tesla did was figuring out all the different ways you could do this. The modern induction motors often have a secondary capacitor circuit. Some of them have what's known as a shaded pole, and I think that's the one that's out there. There's a whole bunch of different ways you can do it, and Tesla thought of a whole range of them and implemented them. Very good question, though.
Other
Add
questions?
anything to that?
Yeah, I think it's actually
This
really
Professor
interesting to
Sullivan's
see.
one of the world experts on power magnetics, by the way. He's probably more qualified to answer than I am.
But it's very impressive to see how quickly Tesla came up with all these different variations of the different possible ways of doing it, many of which are still in use.
In fact, some of the GE guys after the fact went out and tried to get some patents on something. Oh, we're going to have a teaser current, or we're going to have some other thing. And basically, Tesla's patents were so basically covered the ground so well, they all got rejected. So then GE basically proceeded to, and Thomson Huston just proceeded to cheat and run over his patents. But that's another story.
Other questions or areas that people want to probe?
I can see some of the slides. I just want to do some research. I'd like to see some of the
Some of the demonstration?
Yeah, or just some slides from the first presentation.
Slides from the first presentation.
Basically, what I'm trying to figure out, if you could like have Tesla's top three inventions, like in terms of impact.
Oh, the number one thing would certainly be the rotating magnetic field and the subsidiary, all the things that followed that about AC machinery. That's certainly absolutely number one. Number two, in terms of, I think, the breadth of things that followed it, is probably his use of tuning and resonance that is mostly applied to radio systems today. And probably, I think it would be hard for me to say which is the most important number three, because from then it devolves into dozens and dozens of ideas that are all, have their place in the world. I mean, keep in mind, he had more than 270 patents, at least, and we don't even know about all of them because they went out in many countries and so forth. But, there's just a tremendous range of ideas that he pursued, from the wireless power transfer to lighting to, he did experiments in X-rays, remote control. He actually had patents on communications techniques later on. that competed with some of the other ones of the day and were progenitors of a lot of communications hardware. So there's tremendous range of things after that, but the top two, I think, would be is exploiting the use of tuning and for electrical means and electrical oscillators, and the rotating magnetic field. And maybe perhaps Professor Sullivan wants to disagree with that assessment.
I would not disagree with that, but I'm actually wanting to check in and see whether we got that question repeated to Bernie properly. I imagine you got the gist of that from Dave's answer, but the question is, what are his top 3 inventions?
I did, and I would completely agree that with Dave's answer about the rotating magnetic field and tuning techniques. The one that I always talk about as well is the idea of multi-phase transmission, that without two or three phase AC, we wouldn't be able to have the huge power systems that we have today, and we wouldn't be able to transmit power efficiently over long distances. And before Tesla, nobody really talked about all AC systems were single-phase systems, and it was only after Tesla came up with his motor and a whole system of transmission that people began to use 2- and 3-phase power.
Yeah, I'm going to agree with that. That does stand above the others, and he had a number of patents on polyphase transmission systems. So yes.
Yeah, so it's really that whole area of the AC transmission, the rotating magnetic field, the different types of AC motors, all that, you can look at each piece and say each piece is a phenomenal invention, but it was also putting all that together and saying that combination of advantages makes this a really attractive way to do things.
I have a colleague who's fond of saying, I'll show you a lot of people with 50 or more patents, and I'll show you almost none who have 2 good ones. And Tesla was one of those. I mean, it wasn't a question of 2 good ones. I mean, the ones we just cited, the few we just cited, but there were dozens of ones that would, in today's world, be considered major key advances because he was able to elaborate all the different kinds of machines and different key ways of doing things that basically put a stranglehold on AC machines and their use in power transmission.
Other questions?
What type of work did you do with X-rays, and what would you postulate you would think of the various modalities that have arisen, like MR and the CAT scan, all these various higher levels of sensitivity for various tissues? Did he have a viewpoint on imaging?
So let me repeat the question first. If the question was more about his work with X-rays and what his vision of where that would go, and then also what he would think of where we have gone with that, with CAT scans and MRI and all of that. Do you want to take that, Bernie?
Sure. So Tesla was always very disappointed that he did not discover X-rays first, because he was actually doing some very similar experiments at the end of 1895 with Geissler tubes and Crookes tubes, and energizing them in various ways. And so when the news broke that Wilhelm Röntgen in Germany had come up with the unexplained phenomena, which were called X-strahlen or X-rays, he was really quite upset. And for the next 6 months, in kind of early 1896, he worked quite hard to basically overcome that disadvantage, and published a whole string of papers on X-rays. Took probably some of the earliest and best X-ray images, which he called shadowgraphs, and he basically realized just how dangerous X-rays were. He basically X-rayed his head for 30 minutes and said that it made him kind of sleepy, but he didn't think it was all that dangerous. But then one of his assistants got badly burned, and he realized just how dangerous they were, and was very cautious about their use. He doesn't really pursue it, and what I argue in the book is the people that actually pursue X-rays as sort of a business are 2 groups. One is General Electric, who can make lots and lots of, they've got all the bulb blowing and manufacturing equipment, so they can make X-ray tubes fairly cheaply. And the other people that get into it are basically instrument makers who can make the electrical apparatus that you need, you know, essentially a small Tesla coil. So I think he looks around, he quickly realizes, I'm not gonna make a big name in this, and he moves out fairly quickly. He would, of course, be very pleased with all the modalities as you pointed out, in terms of using all sorts of electromagnetic radiation to get imaging, because that was the sort of, you know, kind of general idea that he was interested in with X-rays. But by mid 1896, he really wants to get on with what he wants to do with wireless power, and also with his ideas for remote control.
I have one other question.
Sure.
Would you say that he was either one of the major contributors or maybe the first person to discover SAR, specific absorption rate?
Specific absorption rate. I think I would, so let me repeat the question, is whether he was one of the first people to measure, discover, or notice specific absorption rate, or the heating of tissue by electromagnetic waves. I don't know, one of you want to talk about that?
I don't know. Yeah, I mean, SAR is sort of a specific term, right? And I have no notion. He certainly noted that you could get heating from heating of bodily fluids from RF waves, and he was one of the first people to do it. And there was some dispute as to whether he or a person in France sort of proposed this first, and he did less with that than other people. But he certainly was one of the first to very high frequencies and very high potentials that could do that, basically generating high power radio waves. But did he do any quantitative studies of its use? I don't know, and I don't know if Bernie has a better answer.
No, he didn't do any sort of systematic study of it. He did notice it. He did argue that he should take priority, and I'm having a moment where I can't think of the French scientist. Darsonoval was the French scientist who was also very early in this sort of in this particular area. Tesla did often emphasize that he thought electricity was the great healer and could solve all sorts of problems, medical problems, and even mental problems. And in fact, he probably used a mild form of electroshock therapy to overcome a depression that he had in 1895.
And just as an aside to that, Tesla's famous for all these demos where he, grabs live generators and does all this stuff. That stuff's highly dangerous. Also going to sleep in front of X-ray machines for half an hour is highly dangerous. So,
do not try this at home.
Do not do this. You'll be unhappy if you do.
Right. The thing that I always tell people about the 250,000 volt demonstrations, which he does, and by grasping one terminal of a high powered Tesla coil, is this one of the tricks that he did use, not a trick, but one of the techniques that he used was he would always hold a brass ball and bring that into contact with the terminal of the Tesla coil, because if something went wrong, then he would drop the ball and break the connection. And I think that people don't realize how careful he actually was in doing all of these demonstrations.
Okay, well, maybe that's a good note of caution to end on before you go out there and see some of these demos. So let's thank our panelists once again for a very interesting discussion. Okay. Yeah, thank you. Yeah, Charlie Sullivan.
Thanks, Bernie. I'm going to hang up on you. Thank you very much for.
Thank you. I enjoyed doing it, and I hope to see you when I'm actually up there in May.
All right. Bye-bye.
Bye.
To turn that off, we have to mute our video.
It actually kind of made me feel a little more like I was there. I could see what the thing was. It was good. It was a feature. And it wasn't taking up much room at all, particularly with the wide format. Somehow you got to lock in on wide format. Well, I guess there's that. Couldn't really tell